let's talk about the hidden guardian of our power grid, its protection system. Honestly, it's less like a machine and more like a living thing, an invisible nervous system that's always on high alert. It's a question we probably don't think about much until the lights go out. A modern power system is unbelievably complex, which also means it's pretty vulnerable. So, what's the real danger when something goes wrong?
Well, the stakes are just incredibly high. A single failure, a tree falling on a line, a piece of equipment malfunctioning, whatever it is, can trigger what's called a fault. And if that fault isn't contained and contained fast, it can cascade, it can spread, threatening a massive, widespread outage.
But here's the thing, that catastrophic failure almost never happens. Why? Because there's an invisible shield, a system of automated reflexes that just springs into action at an almost unbelievable speed. It stops the damage before it can spread. And that's exactly what we're going to dive into. Okay, so first, let's just get a sense of the scale here. We all know the power grid is our electrical lifeline, and that's not an exaggeration. When we picture the grid, we think of the huge stuff you can actually see, right? The massive power plants, those giant transformers, the endless towers and high voltage lines. But the source material for this explainer points out that the real magic, the thing that actually guarantees reliability, is a part we never, ever see: protective relaying. So let's talk about the problem this whole system is built to solve. What actually happens when the grid is, for lack of a better word, under attack? A fault, or a short circuit, is basically an electrical wound. It's an accidental path for electricity to take, and that causes a colossal, unimaginable surge of current. This surge is so powerful, it's incredibly destructive. It can literally melt metal conductors, destroy millions of dollars of equipment, and just completely destabilize the grid. And this really gets to the core reason this technology exists. As our source, the art and science of protective relaying, puts it, just hoping that equipment will never fail is a recipe for absolute disaster. Designing a system just for normal operation would lead to, and I'm quoting here, intolerable outages. You have to plan for failure. And this is where all that planning really pays off. The solution is this incredibly elegant system that acts just like the grid's own central nervous system. So what is protective relaying? Well, it's a whole network of smart devices. These are the relays, and they have two main jobs. First, they sense when and where a fault happens. And second, they instantly send a signal to open circuit breakers and surgically isolate only the damaged part. The goal isn't just stopping the fault, it's doing it with the absolute minimum disruption to everyone else. The way it does this is pretty brilliant. The system creates what are called zones of protection around every single major piece of equipment. Each generator, each transformer, each transmission line, they're all inside their own little protective bubble, constantly being monitored. And these zones even overlap, so there are absolutely no blind spots. And the precision here is just amazing. If a fault happens in, say, the transmission line zone, the relays for that zone tell only its dedicated circuit breakers to open. The rest of the grid keeps humming along like nothing ever happened. This is what prevents a single failure from taking down an entire city. We've talked about how precise this system is, but the other critical element here is speed. This isn't just a response, it's a reflex, and it operates at a truly mind-boggling pace. Okay, check this out. The response is practically instantaneous. The moment a fault occurs, the clock starts. Within just 1/100th of a second, the relays detect the problem. By 5/100ths of a second, which the source calls high-speed operation, the relay has already made its decision and sent the command to trip. And by 1/10th of a second, these massive circuit breakers have swung open and the danger is completely over. So let that sink in for a second. The entire protective sequence, from the moment disaster strikes to the problem being completely isolated, is finished in less time than it takes you to blink your eyes. It's this incredible automated action of speed and power happening all the time, completely unseen, just to keep our grid stable. Okay, but what if that first line of defense fails? I mean, nothing is perfect, right? A truly reliable system always has a plan B. And for the grid, that's called backup relaying. Think of it this way. Primary relaying is the first responder on the scene. It's super fast and super precise. But if it fails for any reason, a bad sensor, a dead battery, who knows, the backup system kicks in. Now, the backup is intentionally slower. It gives the primary system a chance to do its job first. But if it has to act, its impact is bigger.
it'll disconnect a larger section of the grid just to be absolutely sure the fault is cleared. It's a trade-off. A slightly larger outage is way better than a catastrophic grid failure.
And this is so important. The source is very, very clear that backup protection is just that, a backup. It's a critical safety net for sure, but it is never, ever a substitute for properly maintaining the primary system. The goal is always for that first line of defense to work perfectly every single time.
So let's bring all this home. Why does this invisible, ultra-fast system matter so much to you and me?
Because this system does way more than just prevent blackouts. By clearing faults so quickly, it maintains the stability of the entire grid. And that stability, according to our source, is what lets us safely push more power through the transmission lines we already have. In other words, smarter, faster protection is one of the most effective ways to increase the capacity of our grid without building tons of new infrastructure. Which leaves us with this final thought. We depend on this invisible system every single day. But as we demand more and more from our grid, with electric vehicles, massive renewable energy projects, and growing cities, how do we make sure its reflexes not only keep up, but actually evolve to get even faster and smarter to handle the challenges of tomorrow?